discuss quantum mechanics and optomechanics. So far we discussed the classical regime, both the linearized and the nonlinear, and now I want to turn to quantum mechanics. And the idea is that along the way we will learn some of the tricks that are needed in general to treat quantum systems. So let's start with the Hamiltonian, which we already had written down. First, it's the Hamiltonian of the optical mode. And there the important part is that there is an interaction with the mechanics. Plus then there is the Hamiltonian of the mechanical mode, and B dagger B is the number of phonons, whereas A dagger A is the number of photons. Plus then there will be additional terms that describe, for example, the fact that you have a laser driving the optical mode, plus some dissipative terms that describe the fact that photons will leak out of the cavity and phonons will be damped away. Okay. Now, what I want to do first is I want to consider the laser drive, and we will take two steps. First of all, the laser drive is at some fixed laser frequency, and I want to eliminate this frequency by going into a rotating frame. And that will yield a Hamiltonian that is no longer time dependent, in contrast to the one I'm going to write down now. And second, once you know the laser drive, you know that there is maybe a large light field amplitude inside the cavity, and then I want to get rid of this light field amplitude simply by considering only the fluctuations around the steady state value. Okay, so these will be the two steps. First, let's look at the Hamiltonian describing the laser drive. Now, what does the laser do? It just drives the optical cavity. So, for example, it tries to create photons inside the optical cavity. That would be the operator A dagger. And for this purpose, it has to bring along a frequency that matches, at least roughly, the frequency of the optical photons. So that would here correspond to term minus I times omega laser times time. So it's a time-dependent driving, and if you remember the time evolution of the A or A dagger operator, then A dagger would evolve according e to the I plus I times the frequency of the optical mode times the time. So these somehow match in frequency if they are resonant, and so this is an important term. Okay. So this, of course, cannot be a Hamiltonian in itself. I need to add the Hermitian conjugate to make it Hermitian. And then, in addition, there will be some drive amplitude. So this omega drive is proportional to the laser amplitude. I could as well have a complex omega drive, then I would have omega here and omega star here. That just introduces a phase of the laser, if I like to have that. Won't be important for our purposes. Okay, but in any case, it's a time-dependent Hamiltonian. And so now we want to get rid of this time dependence. So the words to use are that we want to go into a frame rotating at the laser frequency. Now, I'll explain how this works in detail, but let me first write down the result because this is completely general. What we have in the beginning is a Hamiltonian that contains the operators A and A dagger, like the one here. And by applying a unitary transformation, which we will discuss, we end up with a Hamiltonian that has the A multiplied by e to the minus I omega Lt, that is similar to the result of the Heisenberg equations of motion, and A dagger correspondingly multiplied by e to the plus I omega Lt. So this is one of the changes, but in addition there will be an extra term, namely I have to subtract h bar omega L A dagger A. Okay. So this you can take as a general rule. It is possible by a unitary transformation to take a Hamiltonian that contains the harmonic oscillator operators A and A dagger and transform it in this way. And the benefit of this procedure will of course be that if, for example, A dagger is multiplied by e to the plus I omega Lt, then this cancels the e to the minus I omega Lt here, so I will get rid of the time dependence completely. In the end, I arrive at a time-independent Hamiltonian, which makes a lot of things much simpler. Okay. So, let's write that down. The drive Hamiltonian becomes simply h bar omega drive times A dagger plus A. And it's then obviously time-independent. That's a good thing. But the second thing is, of course, I have to take into account this extra term. I will be able to combine it with the original Hamiltonian of the photons. So originally it was photon energy times photon number, and now this turns into something containing the difference between photon frequency and laser. And now if you remember our definitions, I defined the detuning as a difference between laser frequency and optical resonance frequency. So this is minus delta. And so overall I get minus h bar delta times the number of photons. Okay. Now, how do you switch into the rotating frame? The idea is you have your Schrödinger equation with a possibly time-dependent Hamiltonian, and now you simply want to apply a unitary transformation. That is, your original state becomes a unitary operator applied to a new state. And then I can insert this above. And now you'll see what happens. I can apply the time derivative to the new wave function. Or else I could apply it to the unitary transformation, which may be time dependent. And now the idea is that this first term already looks almost like the left-hand side of a Schrödinger equation, except for I have to get rid of the unitary transformation, which I can do by multiplying from the left with the inverse. Or the inverse of a unitary transformation is just u dagger. So this is one part, plus I will bring the time derivative acting on the unitary transformation to the right hand side, and again it has to be multiplied with the inverse. So what I end up with is the result you may know from your quantum mechanics lectures, that the new Hamiltonian is the unitary transformation of the old Hamiltonian plus this extra term that comes from having a time-dependent unitary transformation. And so now the question is just, in our case, what is the unitary transformation to apply? And that is very simple. That is simply an exponential containing the photon number. And so it's really e to the minus I times the laser frequency times the photon number times the time. So this is the unitary transformation that does the trick. And in particular, since the Hamiltonian simply only contains A and A dagger, I have to find out what would the unitary transformation yield when I apply it to either A or A dagger. Okay, so this is something which you can write down by inspection. First, I apply to the right e to the minus I omega L times the photon number times the time. Okay? Then I destroy a photon, and then I apply e to the plus I omega L times the photon number times the time. So I almost apply the inverse phase factor, except for the fact that in the meantime I have destroyed a photon. So in the beginning I apply e to the minus I omega L n times t. In the end I apply e to the plus I omega L n minus 1 times t. So something remains, and what remains is simply that I have e to the minus I omega Lt remaining. And so of course for A dagger the result is the same, except I get a plus here. Okay. So that brings about the transformation I talked about, and if you look carefully, the second term brings about exactly the shift in the frequency that we talked about. So the time derivative of the unitary transformation would bring in omega L times A dagger A downstairs. Okay. And so what you get in the end is exactly the relation we had. So the next thing I want to do is, after having gotten rid of the time dependence, I want to get rid of the overall average value of A. So I want to shift away this part. Or in other words, you could say, I only want to consider the fluctuations of the photon amplitude around the steady state value. And the steady state value I will call alpha bar. Alpha reminds you of the complex amplitude of a coherent state, and alpha bar is just to denote the steady state. Okay. Now, how to find the steady state and which are the equations to solve? Let me write down the Heisenberg equations for A. So, if you work out the commutator with the Hamiltonian, the first thing that arises is the usual frequency term. If we had the original harmonic oscillator, it would be minus I omega A on the right hand side, remember? And now we had a frequency that looked like minus delta in the new frame, so I get plus I delta A. Okay, so this is the first part. And then it turns out that if you work out the action of the drive, again, insert the drive Hamiltonian, this just yields minus I omega drive, simply from the commutator. So that would be the equation if I only had the drive and the coherent evolution. But the point is, of course, if that is the case and then I drive at resonance, I will pump more and more and more energy into my oscillator, so that can't really be true. And in the end, of course, the steady state value will be determined by the balance between the incoming energy from the laser and photons again leaking out of the cavity. So we need to keep the cavity damping, we need to keep the photon decay. Yeah? And so now I will just write down the terms that appear in the Heisenberg equations of motion if you take into account the photon decay and the coupling to this electromagnetic environment outside the cavity. So the first thing you already know, we already used this when we looked at the classical equations of motion. This is a simple decay at a rate kappa half. Kappa would be the intensity decay rate, kappa half is the amplitude decay rate. But this can't be everything, because as a matter of fact, the coherent evolution would, of course, conserve the commutators. It would make A, A dagger equals 1 at all times. But if I simply add a decay, then the same decay term would also enter the equation for A dagger, and overall this commutator would decay like e to the minus kappa t. This can't be true, because the time evolution, any time evolution in quantum mechanics must preserve the commutators. So the resolution of this puzzle is that just like in classical statistical mechanics, if you have some damping, then the damping comes about because you couple to some environment. In this case, it would be all the electromagnetic modes outside of the cavity. If you couple to an environment, there is not only damping, but there are also fluctuations coming in from the environment, a fluctuating force. In classical statistical mechanics, this would be a thermal fluctuating force, and its strength would be determined by the temperature. But even at zero temperature, in a correct quantum description, there is a fluctuating force. It's called zero-point fluctuations usually. And so in this case, there will be an additional term, and depending on how you normalize the operators, it may look like this, namely square root of kappa times some fluctuating A in. So these would be the zero-point fluctuations that enter the cavity from the outside. And so their purpose in terms of this commutator is always to replenish the commutator, so to speak. A and A dagger would decay, but then there are these extra fluctuations coming in, and if you work everything out, and if A in has the right properties, then the commutator will be preserved. So the equation as it stands here is a part of a general framework that is called input-output theory. And which describes how you should treat an open quantum system like this cavity. There are fluctuations coming in from the outside, and then you could also treat the field being emitted by the cavity to the outside world. Now, I'm not going to derive this, but if you want to read that up, there is a good book by Gardiner and Soller. A book on quantum noise. And also you can find these things and more in a review which we wrote recently. So that would be Ash Clark et al. In Reviews of Modern Physics this year. Okay. I just wanted to indicate the structure of the equations. But now we can concentrate on the average value. And by the way, what I wrote down here is of course without the mechanics. Let's now focus on the average value. That is, I take the expectation value on all sides of the equation. And if I take the expectation value, the purpose of this is of course just to get rid of the fluctuations, because the expectation value of the fluctuations will be zero, just like in classical statistical mechanics. So if I call the expectation value in general alpha, then I would have alpha dot equals I delta minus kappa half times alpha minus I omega drive. Okay. And now if I demand that I'm in steady state, then I can simply solve this equation and I obtain alpha bar equals I times this driving amplitude divided by I delta minus kappa half. And so it wouldn't be difficult to generalize this in the presence of a mechanical structure if the mechanical structure is at rest, or if I only care about the mean value. Because then what would happen is that the detuning only is replaced by the effective detuning, which we already introduced, which has the additional shift brought about by the mechanics. And now it's easy to see what to do. We have arrived at the steady state value that takes into account the drive, and the idea, as I said before, is to shift away the drive. So I would say that I get a new A, which is the old A minus alpha bar. And now, if I look into these things and write down the equation of motion in terms of the new A, I would get exactly the same equation of motion, except for one thing, that the omega drive drops out, because this has already been taken into account by the steady state value. And so I can then easily write down the Hamiltonian for the new A, I only have to remember that I have to switch off the drive, so to speak, because it has already been taken into account. And in order to save writing, of course, I will apply the same confusing trigger notation as always. In the following, I will call a new A. Okay, so you will have to remember that the A which we are talking about from now on is already the shifted A. The A we are talking about from now on is only the small fluctuation part. Okay. So now let's try to represent the state of affairs graphically. So what I want to plot is somehow the complex plane of the light amplitude. So if I were talking about coherent states, I would plot real part of alpha and imaginary part of alpha. But I can as well, at least symbolically, say that I'm interested in, so to speak, the real part of A, which would be 1/2 A plus A dagger. And I want to indicate this is the as yet unshifted A. And the imaginary part. Okay. And the idea is then that the laser drive will induce a steady state value with a complex amplitude alpha bar. And around that steady state value, there are always fluctuations, and they are described by the new A. And we already learned the same kind of story and language in the case of the Wigner density. And so we learned that if I just have a driven harmonic oscillator, I would expect a coherent state. A coherent state is determined by this large complex amplitude plus fluctuations that have a size given by the ground state size. Okay. And so now I can write down the Hamiltonian. Okay, so how does it look like? First there's the minus h bar delta times A dagger A. There will be no driving term. There will be, of course, the mechanical harmonic oscillator. Plus, there will be the coupling term, which in complete notation reads minus h bar omega optical divided by L. This is one part. Times A dagger A, but now I have to be careful. It's still the old A dagger A, the complete photon number. And we will learn what that translates into in a moment. So it's A old dagger A old times X. And X I already want to write in terms of phonon operators, so I want to insert 0-point fluctuation amplitude times B plus B dagger. Okay. There's no driving term, but there is still dissipation. For example, the mechanical oscillator is still damped, plus the photon operator, even the shifted photon operator, is damped because of coupling to the environment. Okay, fine. So now let's focus on the full photon number. Well, of course, I know the A operator, the original A operator is the steady state amplitude plus my little fluctuation part. And now the calculation will be very typical. The same occurs, for example, when people in laser physics talk about homodyne detection. The idea is that you have a large part, this is the steady state part, plus a small amplitude. And you want to calculate the intensity. So there will be a direct term, alpha bar squared. That's the large intensity. Plus, there will be cross terms like alpha bar star A plus alpha bar R A dagger. So these are the cross terms, and these will be the important ones that we want to keep. Plus, finally, there is a term A dagger A, and that is a term which we want to discuss away. Now let's discuss these terms. First, alpha bar squared. This is just a fixed steady state amplitude, it's a classical number. It would be multiplied with the x operator. It corresponds therefore to an average extra force that will displace the mechanical oscillator a little bit, but no more. Yeah. So the effect is very simple. So in the following I will assume that whenever I talk about my steady state displacement x bar, this effect has already been taken into account, so then I can omit it here. Okay. And the second term, that's the important one, and so I want to write it down including all the parameters. So first look at the structure. It's some constant times something that looks like A plus A dagger times B plus B dagger. So it's a very simple quadratic coupling between two harmonic oscillators. Depending on whether alpha bar is real valued or imaginary valued or complex, this will correspond to the position or to the momentum or to some linear combination. But since I can always undergo a unitary transformation that changes position and momentum and so on, I will take the freedom and say that alpha bar in the following will be real valued. This really doesn't change anything. I can always arrange things such that this is true. So then I end up with a term that looks like minus h bar g times A plus A dagger times B plus B dagger. And the g I can immediately read off. This is the important coupling constant. It contains photon energy divided by cavity length times 0 point fluctuations of the mechanical structure times alpha bar, and alpha bar of course is nothing but the steady state light field amplitude, and that would be the square root of the photon number. Okay, so this is the linearized optomechanical coupling constant. linearized in the following sense that I will have linear equations of motion from now on. And it's important to remember that the square root of the photon number appears only because initially I had an A dagger A, and then I looked at the cross term, and in the cross term I had the light field amplitude. And that is important because it's an enhancement. I can now simply turn on the laser power and increase alpha bar as far as I like in principle. And so by that I can tune the coupling constant G, simply by changing the laser intensity. So that's interesting and important, but it only works for this approximation where you only keep the quadratic part of the interaction. It would not work if you were to consider, say, the interaction between one photon and one phonon. Then there is no such enhancement. Okay. And finally, of course, I have to discuss away the A dagger A term. And that I can do simply by pointing out that alpha bar is supposed to be much larger than 1, whereas A dagger A, in the regime where I have only 0 or 1 extra photons on average, will be on the order of 1. Yeah. So this term will be larger by a factor of alpha bar. So we want to neglect this term because, roughly speaking, A dagger A over this alpha bar A plus A dagger term, that goes like 1 over alpha bar and is much less than 1. So again, A here is already the shifted operator. It does no longer contain the large amplitude alpha bar. So, for example, if you switch on the laser and don't take into account the interaction with the mechanics, then the optical cavity will end up in a coherent state. And in the coherent state, of course, there's this large amplitude alpha bar, but this has been taken account of. And A then corresponds to a harmonic oscillator that is in the ground state. The shifted ground state corresponds to the coherent state that the laser produces. Okay. So again, in total, we get the linearized optomechanical Hamiltonian. So that is minus h bar delta A dagger A plus h bar omega times the phonon number minus h bar G A plus A dagger B plus B dagger. And that's the important interaction. So you can draw a picture and say, we have the operator A that describes the photons, so that's the optical cavity. And there's the operator B describing the phonons, that is the mechanics. And then as we see these two oscillators interact via some strength G. But that's not everything. I also want to indicate what are the dissipation processes. And so for B, for the mechanics, we know there is some damping gamma, some damping rate gamma, and that quantifies the coupling strength towards some environment, which is simply the mechanical support on the phonons in the structure, and that is at some bulk temperature T. Yeah. Even the photons feel some dissipation because they can decay at a rate kappa. The environment they couple to is the electromagnetic vacuum outside the cavity. And now, again, you can ask, what is the effective temperature? But since these are optical frequencies, without any laser drive, there won't be any thermal fluctuations, because optical frequencies are much higher than room temperature. So that's essentially T equals 0. And then in addition, of course, there's also the laser drive. And the way we wrote things here, this laser drive has already been taken care of and just resulted in the value of the coupling constant G. Okay, so the mechanics, of course, has a frequency capital omega, that's clear. The optical cavity in this rotating frame has a frequency minus delta, minus the detuning. Now, if the detuning is negative, this is a positive frequency and everything corresponds to the standard coupling between two harmonic oscillators with possibly different frequencies, then you can discuss several cases whether they are in resonance or not, and whether the G is large or small with respect to the detuning and so on. If, on the other hand, delta is positive, that is, if we are blue detuned, then you have the very curious situation of formally having a harmonic oscillator with a negative frequency, with a negative frequency appearing in the Hamiltonian. That is very strange. And you remember, of course, from the classical analysis that the blue detuned case, delta larger than 0, corresponds to the self-induced oscillations, to the instability. And so that is part of the story. But for the moment, let us just focus on the red detuned case, that is delta less than 0. So this is a simple harmonic oscillator. And then we want to discuss the following question. This optical cavity is a harmonic oscillator that by itself would be in equilibrium with a temperature 0 bath. In other words, very simply, if I don't couple to the mechanics, it would just contain 0 photons. 0 photons despite the laser drive, because remember A is the shifted operator. Okay. So this is a very cold oscillator. And this, of course, is a mechanical oscillator that is in connection with bath at temperature T, which may be room temperature, 300 Kelvin, which may lead to 1 million or 1 billion phonons inside the mechanical oscillator. So we have a very hot mechanical oscillator coupled to a very cold optical driven oscillator. And the question is, what does this result in? Well, the answer is, of course, one which we have already given partially, namely that the cold oscillator drags down the temperature of the hot oscillator, so that is the optomechanical cooling, in other words. But what this model now can give us is some insight into whether we can easily cool the mechanics down to zero temperature, that is into the ground state, or whether there is some limit. We will find there is some limit that depends on omega and kappa, mechanical frequency and the photon decay rate. There is some limit to how low you can go into in terms of phonon numbers. Okay, so let's briefly discuss this. And of course the discussion is really far more general than this optomechanical case. For example, the same applies if you have atoms or ions inside an optical cavity, then you can also use this cooling scheme and the mathematics would be exactly the same. So as I said, for cooling we need a red detuned laser beam. In other words, our detuning is negative. But in the picture we just gave, this corresponds to the driven optical cavity being a standard oscillator with a positive frequency. Now, what I want to calculate is what happens to the mechanical oscillator under the influence of the optical cavity. And I already anticipate that it will just undergo relaxation and maybe also a little bit of heating. That is, I want to calculate golden rule transition rates. For example, if the mechanical oscillator is in the one phonon state, there will be a rate at which it decays down to 0 phonons. I call this rate gamma down. But if it is already in the ground state, then it might, very rarely maybe, obtain some energy from the optical cavity and go up. And in the end, it will be the balance of these two rates that determines what happens. And hopefully, and this will turn out to be true in the red detuned case, the down rate is larger than the up rate, otherwise it would be bad. In the blue detuned rate, in the blue detuned case, it's exactly the opposite, and then we have this explosion. Okay. So now we have the general case that we once discussed, that we have a quantum system with some Hamiltonian that I don't specify, that couples to some environment. So X would be the system operator and F would be the fluctuating operator belonging to the environment. And then I said that I can calculate golden rule rates within the system, transition rates within the system, from some initial state to some final state, by taking the matrix element of the system operator between these two system states squared, multiplied with the spectrum of the fluctuating operator. And I should evaluate the spectrum at a frequency given by the difference in energies. So again, this is a very, very useful formula. So that formula is general, and the spectrum, just to remind you, was defined as the Fourier transform of the correlator. So now, let's apply this to our particular situation. In our particular case, the interaction is minus h by g times b plus b dagger, that is the system operator, because the mechanical system is my quantum system, times a plus a dagger, that is the fluctuating environment operator, so to speak. And so, for example, let's calculate the down rate, which is obviously important for grooving. So that would be 1 over h bar squared times the transition matrix element between the 1 phonon state and the 0 phonon state. Now, what is my system operator? Well, I can say all of this is my system operator, so h bar g times b plus b dagger. And then I have to take the spectrum of a plus a dagger, which is f. And what's the frequency? Well, I go downwards, so the initial energy is higher than the final energy, I get a positive frequency, and it's just the energy splitting of the harmonic oscillator, that is capital omega. Now, here I can annihilate one phonon simply by acting on it with B. The matrix element is 1. I still retain h bar g. I square it, so that would give a g square overall. And now, what about this spectrum? Well, again, the spectrum would be the Fourier transform of the correlator. So here I would have a plus a dagger, and again a plus a dagger. Now the point is that what is the expectation value I refer everything to? Well, it's the expectation value for the steady state of my driven optical cavity, but remember that a is already the displaced operator, so that is simply the ground state. It's the expectation value in the ground state. And now, if I have things like a dagger t, a of 0, with respect to the ground state, that is simply 0, because if the photon annihilation operator acts on the ground state, it's 0. So many of the terms will just give 0. There's only one single term that does not give 0. And that is, if I act with a dagger on the right, then even though I'm in the ground state, first I create a photon, and then I can annihilate the photon again to go back to the ground state. To get a non-vanishing expectation value, I have to go back to the ground state. So that's why a dagger is not good. Okay, so the spectrum I really have to calculate is, in this case, only the spectrum a dagger of omega. And again, the notation means take a of t and a dagger of 0 and take the Fourier transform. So you see that this way of calculating transition rates is a very convenient notation. Good. So the next thing we have to do is really calculate the spectrum, and for that I need to calculate the correlator. And the little trick is that I still need to take into account that my optical cavity is coupled to the outside world, that there is this decay kappa that will enter the correlator. Okay, so the spectrum I want to evaluate, I get if I know what is A of t, A dagger of 0. Now, A dagger of 0 is just a given operator, and the idea is now to express A of t in terms of A of 0. And then I can easily calculate the expectation value. Now with respect to A of t, I wrote down the Heisenberg equation of motion, including this damping term. Yeah? So A of t is really A of 0 times, well, in the absence of damping there would be this simple oscillating phase evolution e to the I delta t, but then there is some damping with a rate kappa half. And so at least for times larger than 0, this is the correct time evolution. It's not everything, there is an extra term because you remember this 0-point fluctuating force coming in from the outside. But that will drop out in a moment when I take the average for my expectation value. So now if I take the expectation value A of t, A dagger of 0, at least for times larger than 0 I can already claim it is e to the I delta t minus kappa half times t times the expectation value A of 0, A dagger of 0. Now again, the expectation value is taken with respect to the ground state. I excite a photon, I destroy the photon. This is just a matrix element of 1. This is true at least for times larger than 0, but then you can convince yourself, for example, by shifting the t from the left to the right, since this is steady state, so A of t, A dagger of 0 is the same as A of 0, A dagger of minus t, that even for t less than 0 this remains correct if I simply insert a magnitude sign here. So it decays in both directions. So that means I can calculate the spectrum simply by taking this Fourier transform. Now, the time integral runs from minus infinity to plus infinity. I would have to split it into 2 parts because of the magnitude sign in the exponent. But I can as well say, aha, I could integrate over positive times, plus I could take the same expression integrated over negative times, which just means that the second part, kappa half times t, remains the same because of the magnitude sign, and the first part would acquire a minus sign. But that is simply the complex conjugate, so I could as well write this is 2 times the real part of the integral from 0 to infinity. Okay. So what is that? This is simply minus 2 times the real part of 1 over the exponent without the time. Okay. Okay, so now we have the frequency spectrum, and again, just to remind you, the rate of downward transitions would be g squared times a dagger, the frequency spectrum we just calculated, evaluated at the mechanical frequency. And the rate of upward transitions, well, that you calculated is just g squared times same spectrum, but evaluated at the negative mechanical frequency. So, in the spirit of the fluctuation spectra that we have drawn previously, if I want to draw the spectrum a dagger as a function of frequency, I will see the following. It is a Lorentzian, the real part of this is a Lorentzian. It is shifted towards minus delta, so that's where the maximum must be, and the width is given by kappa. And so now we learned that the downward transition rate would be obtained if I take this spectrum and evaluate it at the mechanical frequency, which makes it anywhere, for example here. And the upward transition rate, which is the reheating rate, so to speak, is the same spectrum but evaluated at minus the mechanical frequency. So what you see here is I have drawn the spectrum for the red detuned case, that is, delta is less than 0. And so this has the consequence that the bulk of the spectrum lies to the right. So the downward transition rate is larger than the upward transition rate. And that is of course good because I want to get cooling. If I were to take the detuning positive, then the peak of the spectrum would shift towards negative frequencies, and then the downward transition rate would be relatively small and the upward transition rate would dominate. Now, what we wanted to calculate is really the phonon number which my mechanical oscillator settles into. So there are these upward transitions and the downward transitions. I want to calculate the average phonon number which it acquires, and I hope that I can suppress this phonon number down to 0. So one way of going about doing this would be setting up a master equation, like we learned before. So we have this extra dissipation mechanism and also heating mechanism, if gamma up is not 0, and we can set up a master equation. In order to set up a master equation, it would be convenient to convince oneself first what happens also for transitions between higher levels. So if I'm in phonon state n and go to n plus 1, what happens then? Well, one can very easily convince oneself that if I go from n to n plus 1, it's just the same old upward transition rate, only multiplied by n plus 1. So this is simply a consequence of the matrix element being square root of n plus 1, and then I square it and I get this. And likewise, if I go down, it's just this downward transition rate, again times n plus 1 in this case. So I can capture all of this by writing down a master equation and I won't even write it down now because we already know the typical Lindblad master equation. The Lindblad master equation always contains just a series of relaxation terms with relaxation operators and damping rates. And now I will have terms with the downward transition connected with B, destroying a phonon, and terms, so this is the relaxation operator, and terms with the upward transition and the corresponding relaxation, or should I say excitation operator, being B dagger. Okay. Plus there would be corresponding other terms that describe the coupling to the equilibrium environment, the mechanical equilibrium environment. But for the moment, let's forget about that. Let's claim that this mechanical equilibrium environment is not really important because this cooling is so strong that we completely overwhelm the coupling to the intrinsic mechanical path. Because we want to see what's the optimum we can achieve, and this is certainly achieved if we overwhelm the coupling to the intrinsic mechanical path. Okay. And again, this is a typical procedure. In the end, you get a simple master equation, but you obtain the transition rates by such a quantum noise approach expressed in terms of the noise spectra. So all the microscopic physics will be in the noise spectra. For example, if you were to calculate spin relaxation in a solid, then you have to specify what are my effective fluctuations, magnetic field fluctuations, say, acting on my spin. Okay. So our question will be, what is the phonon number in the steady state? Well, it turns out that if the master equation is of this type, then you automatically will get a thermal type steady state, that is with a Boltzmann distribution. Only what remains to be seen is what is the effective temperature. So there's a large population in the ground state, smaller population in the excited levels. So it's easy to show it's a Boltzmann distribution. The question is, what is the effective temperature? Well, if this is a Boltzmann distribution, then the ratio between the occupation probabilities is given by h bar omega divided by kBt. So P1 over P0 would be equal to e to the minus h bar omega, that's the energy difference, divided by kBt. Now, in steady state, I know that P0 times gamma up, these are the upward transitions from down here, have to balance the downward transitions coming from above. So that in total there's no net flow of probability. So P0 times gamma up equals P1 times gamma down. Or alternatively, if I look at the ratio, P1 over P0 equals gamma up divided by gamma down. And so now, of course, I know we just calculated our transition rates. That was, the up transition rate was the spectrum evaluated at minus the mechanical frequency divided by the spectrum then for the downward transition rate at the positive mechanical frequency. Okay. So that is relatively simple. And I want to point out one thing. The gammas individually depended on g squared. G squared, for example, depended on the laser intensity. That is the only place where the laser intensity really enters. Here we got the ratio, which no longer depends on g. So it also does not any longer depend on the laser intensity. So that is the simple point, that the minimum phonon number which we will be able to reach does not depend on the laser intensity. It's really the phonon number you reach if you crank up the laser intensity so strongly that you completely overwhelm the intrinsic coupling to the intrinsic mechanical path, and then you reach this limiting value. Okay, so now if you insert the spectrum we just had, then this ratio becomes delta plus omega squared plus kappa half squared divided by delta minus omega squared. So it does depend on the detuning, and you have to pick a clever choice of detuning. Let's do that in a moment, trying to optimize the detuning. But the other question is, well, if I know this effective temperature up here, then how would I extract the average phonon number? Because sometimes this is a better quantity to look at, especially if you are already near the ground state, than the effective temperature. And so it turns out, if you think about it, that this ratio, that this exponent, e to the minus energy divided by kBt, is also simply the average phonon number divided by the average phonon number plus 1. And n bar is the average phonon number in steady state in my mechanical oscillator. So now all that remains to be done if you really want to cool down is that you try to optimize things. You want to minimize n bar, and this really means minimizing the right-hand side. Making the ratio of upward to downward transitions as small as possible. If there are only downward transitions left, you will surely end up in the ground state. And so there is no general answer of what is the best choice for delta, but we can look at a limiting regime. I mean, there is no general simple answer. Of course, you can just do the curve discussion and find the optimum delta. So let's pick a regime which will turn out to be the relevant one anyway, which is when kappa, the optical decay rate, is really much smaller than the mechanical frequency. And that is a regime which we already discussed once, that is called the resolved sideband limit. So if you are in that limit, it turns out that minimizing the ratio is very simple. Namely, you just want to pick delta equals minus omega. Because delta equals minus omega minimizes the numerator. It makes this first part 0, and kappa is a small number anyway. And this then will be like 2 omega squared, that is 4 omega squared. Okay. And so in this regime, it turns out that the minimum phonon number is really given by kappa divided by 4 times the mechanical frequency, and taking this squared. So you see, again, the coupling doesn't enter, the laser intensity doesn't enter. Everything that enters is the ratio between the cavity decay rate and the frequency. And in order to make this really much smaller than 1, so to go to the ground state, you want to have kappa sufficiently larger, smaller than omega. Okay, so finally let me just discuss the experimental situation in terms of this equality. And such quantum limits are also known, say, from atom cooling. Depending on the scheme you are in, you are limited typically by some line widths, just as here kappa is the optical line width of the cavity. So what is the experimental situation currently? What I want to plot on one axis is really the phonon number they have reached. And let me plot this in a logarithmic scale. So 1 is here, then there's 10, 100, and so on. I should add more because often they start with the billions. Then I go to 0.1, 0.01, and so on. Now here on this axis I want to plot the one single parameter that we have, the one single dimensionless parameter that these things depend on, which is the ratio omega over kappa. And now apparently, in order to be in the resolved sideband limit, this ratio has to be larger than 1. And then we have the simple law for the minimum phonon number, which would look like a line if I have a log loop. And then it turns into another slope up here. But the important point is, here you could reach down to basically 0 occupation number. And the question is, where are the experiments? where they typically start at very high phonon numbers. For example, if they are at room temperature and just have 100 megahertz, then you have really many phonons in there, and then they cool down. And the ratio between initial and final temperature, or initial and final phonon number, can reach on the order of, say, 10 to the 5 or so. And now if you start at a lower temperature to start with, and you make sure you have a larger mechanical frequency or a smaller kappa, then you are somewhere here, and you might have a chance of reaching down towards the ground state. And currently, that is in 2010, they are at about, say, 10 or so quanta. And so finally, just to complete this discussion, this is the minimum phonon number you could reach. What happens if you couple both to this driven optical cavity and to the intrinsic mechanical bath? Well, then it turns out that n bar is just a weighted average. So you have the optomechanical damping rate times this minimum number plus gamma, the intrinsic mechanical damping rate, times the thermal number of the environment, then divided by the sum of these two rates. And it turns out that the optomechanical damping rate, which we calculated previously, is just the difference between the downward and the upward transition rates that we calculated just now. Okay. So that would be the general expression, and that you would use in order to calculate which laser power would I need in order to go to such and such a phenomenon. Okay, so that was an example of a quantum system driven out of equilibrium, where you could cool by this non-equilibrium drive. And there are other examples that are very similar. For example, if you have some superconducting circuit of the right kind, pass a current through it, and then say couple it to a nanomechanical oscillator or other devices, then you can also cool in a similar fashion. So it is quite generic to be able to cool by a non-equilibrium drive of a quantum system. And this driven quantum system can act as a bath for another quantum system and cool that quantum system. Okay, any questions? Yeah.
So how do they measure the temperature or the number of photons in the mechanical?
Okay, so how do they measure the number of phonons? Right now, they don't really measure the phonon number directly. What they really do is they take this displacement measurement, which we discussed roughly in the beginning. So they look at the phase shift, they look at the spectrum of the phase shift fluctuations, which is the same as the spectrum of the position fluctuations. Then they find these Lorentzian peaks, and then they take the area, and so they deduce the temperature from the area under the peak of the displacement spectrum. And that's what they do. Okay, so see you.